some ice ages. Well, we're in an ice age now, but some snowball Earth situations, and then some very, very hot situations. And I'm going to talk a little bit about sort of what broadly...
Lower the lights.
Yeah. Step up. And so I'm going to talk a little bit about sort of what the feedbacks are and kind of what drives some of those climate changes on a very long time scale, millions of years, and then eventually get to what are called Milankovitch cycles, which is sort of this periodic oscillation between glacial and interglacial periods, so times like at the last glacial maximum when there was ice about a kilometer thick standing right where we are now, and then interglacial times where we're happily ice-free and hanging out and driving along the lake shore. So I'm going to talk sort of about current best theories for sort of what's driving those cycles between the glacial period and the interglacial period. And those are actually very small changes in orbital parameters. So we'll be kind of tying it back into what Tom will be getting to with sort of how orbits are set up and some of the small variations in the orbit as time evolves. And feel free to interrupt with questions as we go along here if you have them, and I'd be happy to answer any questions at the end as well. So the habitable zone is sort of loosely defined as a range of distances from the sun where a planet can have liquid water present. So the surface temperature needs to be somewhere between 0 and 100 degrees Celsius on average, globally averaged. And that's going to depend on the size of the sun, the temperature of the sun, so how much energy that sun's emitting. It's going to depend on something called the albedo of a planet, which is just how much energy is reflected off of the surface of the planet. And then it's also going to depend on the atmosphere of the planet. And so an atmosphere can kind of trap outgoing energy and re-radiate it down towards the solid planet, and that can sort of make the ground temperature warmer than one would assume otherwise. So this is just sort of the various different orbits of the planets drawn out here. And then up top is the flux of energy received at the surface in watts per meter squared for each of these, for each of our planets. And right here in blue is Earth. And you can see that it sort of decays away as you get further and further away. And so that's just because as you move further away from the sun radiates its energy equally in all directions. And so the flux, as you move further away from the sun, decreases as the square of the distance away from the sun. But we're sitting here at a distance of 1 astronomical unit, and our flux is somewhere, well, it's about 1,366 watts per square meter at the top of the atmosphere.
How much does that vary?
We're going to get to that. It's varied over time quite a bit. The sun was cooler when it first formed than it is now, and it varies some based on these orbital parameters. That's on the order of 3 or 4 watts per square meter. It's not a ton. And then there are even smaller variations that come from solar spots and various different cycles like that, but I think that's quite small. So to try to take sort of that number of 1366 and figure out what the temperature would be, or sort of what your first guess of what the temperature could be on the surface of the planet, you need to figure out how much energy is actually hitting the planet Earth. And so there, it's just sort of the cross-section of Earth is what's capturing some of the energy being emitted by the sun. And so you can calculate all of that, and that's sort of represented here as the input sort of circle. But the energy is then emitted from the planet as a black body, and it's emitted over the whole sphere. So this is your flux leaving Earth is proportional to the temperature on the surface. This is the Boltzmann law, Stefan-Boltzmann law, times some constant, which is denoted as sigma, times temperature to the fourth. So you can sort of sum up all of the energy that's hitting that circle here, the cross-sectional area, and set it equal to all the energy that's being radiated across the sphere, which is here. And then you can solve for the temperature. And so we can do this. But first, we need to take one quick step back. And I said that this isn't quite right. It's not the flux at the point in our orbit, because Earth isn't a perfect black body in the visible spectrum. So the sun is very, very hot, and it emits light in the visible spectrum predominantly. I mean, it has a very broad wavelength, but Earth has an albedo of about 0.3. So it absorbs 70% of the light that hits it. Fresh snow has an albedo of maybe 0.8, 0.9. Water actually has a wider range than is shown here. I forgot to change that, but some of that contrast in color that I showed you in that first slide with the superglacial lake comes from the contrast in albedo between water and ice. And so there's a wide variety of different albedos that make up the planet, but when you add it all together, a good estimate is about 0.3. So that means that instead of dealing with sort of summing 1,366 watts per meter squared over the cross-sectional area of Earth, you're only going to sum sort of 950 or so watts per meter squared. So we can take that equation that I showed you of flux in equals 4 sigma t to the fourth, and sort of solve it for temperature, but instead just try to figure out over what regions we'll find a temperature that is in the range of 0 to 100 degrees Celsius. And that's what's shown here for a planet Earth without an atmosphere, which without an atmosphere would be hard to have standing water anyway. But without an atmosphere and with a planetary albedo of 0.3. And it's very, very clear from this picture here that Earth is sitting outside of this green zone, which is where we want to be if we want to be hanging out and not frozen. So clearly there's something going on here that isn't captured in that very simple model, and I've sort of been hinting at it, that it's this no atmosphere part. So this comes from what I was saying earlier, that the sun radiates, it's very hot, and it radiates in the visible. So we have this shortwave radiation incident on planet Earth, but Earth's temperature is cooler, and it radiates more in the long wave, infrared. And so you see it radiating back out here in the blue. And our atmosphere is very convenient in that it is transparent to shortwave radiation. Shortwave radiation passes through very easily and hits the surface, but long-wave radiation gets absorbed by the atmosphere. And so we're going to do sort of a simplest model of an atmosphere that you could do, and assume that there's just a single layer, some distance not too far from the surface, and that layer absorbs all outgoing infrared radiation, but allows all incoming shortwave radiation or reflected shortwave radiation to pass freely. This is sort of a more extreme example than our actual atmosphere. Our actual atmosphere is sort of what's called a gray body. So it lets some infrared leak out. It's not a perfect greenhouse. And this is why we're concerned with changes in greenhouse concentrations, because there's room. If we had a perfect greenhouse already, then we wouldn't care if CO2 or water vapor increased in the atmosphere, because it wouldn't make any difference, because it was already absorbing everything that was trying to leave. Going back to sort of what I showed earlier, to get this function for the incoming energy at the surface from the sun to a temperature, we have a flux coming in from the sun, and just as we did originally, that has to be balanced by a flux going out. But in this case, the flux going out needs to be the flux going out from the atmosphere layer, because that's sort of the final layer that's emitting towards space. So those have to be in balance. You always have to balance energy in any kind of a problem. So there's our energy balances out at the very surface, or at the very edge of the atmosphere. But the atmosphere, like everything else, is going to radiate in all directions. And in this case, the atmosphere can radiate both out and in towards the planet. So you get sort of this extra short or long wave radiation coming in towards the ground, just as you have the short wave radiation coming in towards the ground. And because the radiation hitting the planet has to equal the flux going out, and because the flux going out has to be the same as the flux going back in towards the planet, you're basically getting 2 times the amount of energy hitting the surface of the planet with this simple greenhouse gas single layer model. So we find here that we get this 2 times the flux going in. And if we then look and see how this affects our idea of a habitable zone, we see happily that this corrects our problem, and we are in fact sitting in a nice warm region relative to where the sun is. So that's for right now. There was a question about sort of changes in that number of 1366 as a flux hitting the top of our atmosphere. And that has in fact changed over time. So this is a plot showing the age of our sun and radiation relative to current radiation of the sun. And you can see that it has decreased, or has increased significantly since sort of the very beginning, and will continue to increase and increase over time. And I don't know much about solar physics, but my understanding is that the sun is burning hydrogen and converting it to helium and other heavier gases, so it's becoming denser. As it becomes denser, it sort of starts to collapse, and then the radiative pressure has to kind of match that to provide a stable sort of pressure in the gas of the sun, and that extra radiative pressure coming out means a hotter sun, basically. But I think all suns sort of do this, all stars do this as they evolve. So we can think and start to wonder whether or not Earth was always in a habitable zone, because there's sort of significantly lower values here earlier in time. And so if we do the same calculation trying to figure out at what distances from the sun you could have a planet that has temperature ranges with which liquid water can be present, we see that we're just sort of barely hanging in there with the sun at 80% of what it is today. And this value is probably sort of reasonable, maybe 80 or 90% of what it is today, earlier in time. But this calculation is done with a very strong greenhouse gas layer. The single layer over predicts the temperature of the planet right now by about 15 degrees. So if you do that same calculation for the single layer with the sun at the current temperature, you get a global average temperature of around 30 degrees Celsius, and our global average temperature is actually more about 14 or 15 degrees Celsius. So the simple model that we're using to try to get a handle on whether or not Earth was always in this habitable zone may be sort of a best case scenario. Also, as you start to get cold, your average albedo would go up because you'll get more ice. And this is something that I'll be talking about a little bit more as we go along here. So while this slide shows that Earth sits happily within that habitable zone, even at early time, it might not be a simple scenario that, it might not be sort of the normal scenario that gets you in there. There might have had to have been something special going on to kind of keep us in the habitable zone. Yeah?
Can you carry out this simple model? Because you need the negative entropy to drive the photosynthesis. You're talking only about energy and not energy within the spectral range that you need. Because I know that the heating up raises entropy and you need to keep it down to have life.
Yeah, I mean, people have certainly done much more complicated models than what I'm doing here. People have taken, there's a new professor over in the geology department who's taken the state-of-the-art climate models and run them for lower insulation values to try to get a handle on what we're going to be getting to here in a minute, but what's called snowball Earth, which are these periods of time about 2 billion years ago when Earth got completely glaciated and basically became a frozen planet. And he's been doing a lot of work trying to understand how you get into, and then more importantly, how you get out of one of these frozen states. And it's using sort of all the bells and whistles that you can throw at the problem.
And I just noticed interestingly in all of these different models, Mars is well outside of the habitable zone in terms of temperature, in terms of the simple model.
Yep. So part of it is that Mars currently has a lower albedo than Earth. So these are for an albedo of 0.3, and if you lower that to sort of a bare rock albedo, that'll help get Mars into the habitable zone.
But if we had no atmosphere anyway, so
yeah. But you know, the thought is that Mars had an atmosphere earlier, and I'll get into some more about kind of how that atmosphere is maintained, hopefully. But yes.
thanks.
These are all just very meant to be more illustrative than definitive. Just from this first bit here, we are living happily in a habitable zone. This idea of a habitable zone is becoming a very hot topic, and a lot of people are thinking about it as they do sort of extrasolar exploration using telescopes, trying to find other planets in other solar systems. And one of the first things they do when they find a planet is try to figure out how far away it is from the sun and how strong that sun is, and try to figure out whether or not that planet is within the habitable zone. Yeah?
I may be way off here, but you said the sun is burning hydrogen, turning it into helium and other heavier gases, so its density is increasing. Is its gravity staying the same? And if it isn't, would that affect the necessary orbit of the planets?
My guess is that its gravity must be changing a tiny bit as it converts mass into energy, but I think it's relatively small. I don't think that the total mass is changing drastically, but I could be wrong.
Energy gravitates as well.
Energy gravitates as well, I guess. Yeah, I'm sure there are some people in this audience who can speak more to that than I can. I'm not sure. I don't know. The habitable zone has changed over time and will continue to change. as the sun evolves. And this is true in other solar systems as well, and something that plays a part in sort of thinking about habitable planets out in other galaxies. Is that, you know, lots of times we're seeing what the planet was like a long time ago, and it may no longer be in the habitable zone if we were to somehow communicate or go there. And so what I'm going to start talking about are some of these internal mechanisms that kind of regulate climate and maybe help to keep us in a very temperate climate. Earth has experienced a very wide range of climates in the past. The two extremes are ice houses and hot houses. So ice houses are where the planet is completely covered in ice or nearly completely covered in ice. And then a hot house is where there is absolutely no ice on the planet. And we currently reside in a sort of in-between state where we have small ice sheets in both northern and southern hemispheres. There are other states where we just had ice sheets in the southern hemisphere and no ice in the northern hemisphere. There's a lot of interest in some of these extreme climates on Earth because they're a great way to kind of test our understanding of how the climate system works. So as we're trying to understand how our climate system is changing right now, one of the really good tests is to take any model you have and throw it into an entirely different climate regime and see if that model produces what we think the climate was like. And so these are people who are trying to use current GCMs to figure out what was going on with snowball Earths, which I'll talk about in a second, and then also with hot houses, when you had very, very warm temperatures even at the poles. So this is sort of a timeline of Earth's history, and there were two major times when we had sort of periods of snowball Earth. One was sort of in the 2.2 million years ago range, and they think that this one was sort of two separate episodes. And then one was a little bit more recent, at sort of 7 million years ago, or 700 million years ago. And this one might have been, might have had a few sort of snowball Earth episodes all kind of fairly close together. The first one I know a little bit more about, and it coincides with sort of the appearance of oxygen in the atmosphere. And so we think that a lot of times, well, so it's difficult to get into a snowball Earth, and it's difficult to get out of a snowball Earth. So it takes a fairly significant hammer whacking the climate system to get you into a snowball Earth and to get you out of one. But the reason it's so hard to get out of one is because as you get into a snowball Earth and the whole planet's covered with ice, you're reflecting maybe now 60% of the energy instead of 30% of the energy incident on the surface. And so you have a lot less energy to heat up the planet, and it makes it very difficult to actually absorb enough energy to melt ice. Yeah?
I was just wondering, does Earth radiate more energy than it receives from its own cooling, the volcanism and stuff?
Yes. Yep. So the Earth radiates, I think the flux is somewhere around 300 watts per square meter, and the geothermal heat flux is more on the order of 30 or 40 watts per square meter.
It's a trivial.
Yeah, it's largely, and it's down to 5 watts per square meter in some places. It depends on how close you are to the magma beneath the surface. Yeah.
What was the whack that got us out of snowball?
So there are a couple of different ideas. And broadly speaking, you have outgassing of CO2 from volcanoes. and you can build up concentrations of CO2 in the atmosphere upwards of 3,000, 10,000 parts per million. We're at 400 right now. And eventually you just get enough CO2 up there that it traps even that small amount of outgoing radiation and you start to melt. There are other ideas that you can have some ice dynamics that could help. There still are going to be, as is sort of illustrated here, desert zones. You're going to have sublimation in some places. So there will be bare rock sort of present, and as that dust blows around, it can slowly accumulate on top of the ice and change the albedo, which can help. This was a long time ago, and the evidence for it is strong enough that we were pretty sure that there were these global glaciations. There could have been kind of a small moat of water, and that would help us get out of it. But sort of the evidence for timing of getting out of it and for the exact mechanism isn't that strong.
You're talking about the first one or both of them?
All of them, yeah. They're all pretty sparsely. But
Could it
largely
impact,
talking about
could it
this.
impact its water?
That is one of the ideas.
Yeah.
Yep. Yeah, I mean, I think they're trying to find ones that you don't have to call on an impact. That's kind of cheating. Like, oh no, an impact hit a big ice sheet, and that's why you don't see any evidence for it. So this is a picture sort of illustrating what a hothouse would have looked like. This is up in the Arctic Circle, and this is an Alaskan Inuit holding a canvas of a North Carolina swamp, or South Carolina swamp, I forget which, but this is sort of what that region would have looked like about 50 million years ago during the Paleoeocene thermal maximum. This was a hot house, and so you have very, very warm, luscious, kind of tropical forests, even up right next to the North Pole. So again, a very, very different climate than what we have today, and very different from an ice house. And the hottest climates tend to happen right after an ice house, because you have to put so much CO2 up into the atmosphere to get out of an ice house that then once the ice is gone, your temperature swing is just going to skyrocket. Yeah.
The chart you had before showed that the average temperature difference between a glaciation period and a hot house was about 100 degrees.
Yeah, close to that. I mean, those are sort of the extremes. Different models can give you different answers, but you're looking at sort of a variation of plus or minus 50 degrees, and this is right around when life was starting to form. And so life was being subjected to these back and forth temperature swings of plus or minus 50 degrees C, and pretty drastic. Yeah?
I thought there was no land in the North Pole. How would you have a forest?
So this isn't quite the North Pole. This would be sort of the north slope of Alaska, or northern parts of Canada and stuff. And so there are these huge tree trunks, sort of fossilized tree trunks up there, and alligator fossils from this time period.
Are there any sub-oscillations to this? Can you see any evidence of it?
Yeah, so that's where we're going to at the end of this talk. Yeah, so especially as the
Could you repeat the question, please?
Yeah, the question was, are there any sort of smaller oscillations inside of this? Yeah, I think that there were probably some oscillations. I don't know. And people see periodic features in rock record and in other sort of indicators of climate during this time period, and they attribute that periodicity to orbital parameters, which is what we're going to get to in a second. But I don't know if that was where your question was going, but I don't know much about that side of things. And I don't know if the climate just sort of oscillates naturally.
So there would be, when you've got a spike there will be swings back and forth, but the same mechanism.
No. So in that case, no. When you go from an ice house to a hot house, it is
One straight.
up and then flat. It's cold, it's up, and you're flat and you're hot. Until, I mean, there's a slow drawdown of CO2 in the atmosphere.
It doesn't oscillate.
But it doesn't oscillate. Nope. Yep. So we're going to zoom in from that longer sort of look at climate into a more recent look. This is going back to about 65 million years ago. And that photo from the hothouse is right around here during the PETM is what it's called, Paleo-Eocene Thermal Maximum. And since that time, this isn't temperature exactly, but it's a proxy for temperature. So you can think about this as temperature on the left axis here, and time along here, and you see this slow drawdown in temperature to present, and then here you see how it gets much more noisy. This is where you start to get into the Ice Age Earth, where you have rapid temperature swings on the order of 100 to 40 to 100,000 year cycles. And so it's relatively constant when it's hot, and then as it gets colder, the data becomes noisier. And this isn't just sort of noisier data, this is the climate actually becomes noisier. So this sort of brings us to thinking about kind of why the climate changes. And I'm going to talk about three main things here. I'm going to try to pick up the pace a tiny bit. I'm going to talk about three main ways that the climate can change. One is through changes in the atmosphere. One is through changes in the albedo. And then one, which I haven't really talked about much, is through changes in heat transport. So this is just the equator receives more energy than the poles, and so you have heat moving from the equator to the poles. And over long time scales, plate tectonics drives a lot of these changes. So over that 65 million year, or over that 2 billion years sort of time history, we think plate tectonics plays a big role in this. One of the biggest sort of long time scale drivers of climate is what's called the silicate weathering feedback. So this is that as you weather silicate rocks, you pull CO2 out of the atmosphere, and that process is temperature dependent. So when it's hot, you're much more efficient at pulling CO2 out of the atmosphere, which brings down your global average temperature. When it's cold, you become inefficient at pulling out CO2 from the atmosphere. The outgassing of CO2 from volcanoes changes slowly over time, and so you can slowly build up CO2 in the atmosphere and bring your temperature back up. So this is sort of thought as an Earth thermostat, basically. It keeps you set within a sort of happy range. But it can change depending on what's being subducted around the world. If you start to subduct more, as you begin to subduct rocks that have a bunch of CO2 stored in them, that will then, down the line, lead to increases in how much CO2 is released. So, this outgassing isn't constant over time with CO2. And so this provides both a feedback, but also sort of a driver of climate change as well in a very, very long term. In sort of a shorter term, long-term to shorter term time scale, changes in the Earth's albedo can significantly change the climate as well. So here we have sort of the amount of Earth present, or the amount of ice present on Earth now, and this is the amount of ice present during the last glacial maximum. All of this extra ice reflects a significant amount of energy, and so you have cooler global temperatures.
Question.
Yeah.
That does precession or figure?
Yep. And that's where we're heading.
Okay.
Yep. That's sort of the end goal is to get to current ice age climate variations, which is all about orbital parameters. This is a slide sort of loosely showing one way that heat transport can change from plate tectonics. So there used to be sort of a path for water to snake its way in between India and Asia, and then up in between Africa and Europe, and in between South America and North America. And so this is very warm water that can just go around the globe and around the globe. As these different passageways closed off, that then forced the water to shoot up north or down south. In most cases here, it would shoot up north because you're kind of well above the equator. And that brings warm water up towards the poles and can directly affect the albedo by just bringing heat and melting ice, but can also affect some other feedbacks in the climate system. So this is sort of broad 65 million year history of climate. Starts off pretty warm with no ice. Something happens and ice starts to grow in Antarctica. Right now, one of the best guesses is that it was the collision of India with Asia and beginning to sort of form the Himalayas. The Himalayas are uplifting tons of nice silicate rock, and the monsoon brings a lot of water and dumps it onto that rock, and so you get a lot of weathering, which can lead to sort of a slow drawdown of CO2 over time. So that's kind of the best idea for why Antarctica started to grow. You also have the opening of a passageway. You have an opening of a passageway right here called Drake's Passageway, which allowed water to flow circumpolar around Antarctica, which kind of isolated Antarctica from the rest of the climate system. As you start to grow ice in Antarctica, the ice begins to reflect more energy, and ice fills sort of Antarctica and then starts to grow in Greenland. And then you transition into this sort of periodic sort of fluctuation in ice levels, which is what we really call our ice age, and these are driven by Milankovitch cycles. So this is the glacial times down here, and the interglacial times up here. Glacial times with more ice, large ice shelves, or ice in the northern hemisphere. So up here is a sediment core. It's showing the same proxy for temperature that we've been talking about in the past. And just to remind you, up top means less ice, and down on the bottom means more ice. These are basically evidence of the isotopic ratio in the bottom boundary or bottom waters in the ocean. These are sediment cores collected from 57 different locations, all stacked on top of each other to try to minimize sort of regional variability or regional effects on this climate record. So you can see that it's sort of a higher period or a higher frequency of oscillation up until about 120 or about 1.2 million years ago, and then that frequency of oscillation starts to slow down from a 40,000 year cycle to a 100,000 year cycle. And yeah.
Oh, it seems to be growing in amplitude.
And it also grows in amplitude. And the changes that we see here could be changes in the temperature of the water at the bottom of the ocean, but that change in the temperature of the water at the bottom of the ocean is too small to explain the magnitude of these oscillations. So it has to be some combination of changes in the temperature and changes in the ice volume. So this is still a good proxy for ice volume globally. So 20,000 years ago, we were at what's called the last glacial maximum, which was the greatest ice extent during the glacial period, the most recent glacial period. And here you have in light gray the Laurentide ice sheet and Greenland ice sheet, and then the Fennoscandia, or yeah, the ice sheet that covered sort of northern Europe and Scandinavia. Those are the three big ones. Antarctica was also larger than it is today in terms of ice volume. And the total amount of what we often refer to as sea level equivalent of ice that was tracked in this larger extent of glaciers on land was about 120 meters of sea level. So sea level was 120 meters lower than it is today. And that change has happened in 20,000 years. The rest of the remaining ice that's stored on land is about another 60 to 70 meters of ice. So we've lost more than half of the ice that was present during the last glacial maximum.
Why did it extend so much further for the North American side?
It was too dry here. There was no water to snow, basically. I think just because the Pacific is much larger, it could pick up more water vapor, and you're dumping it on Greenland and then Europe. And I mean, even still today, this is very cold, but there's very little snow up in Siberia. So we're going to go through sort of the three main orbital parameters that we think sort of add up to cause this variation in insolation, which somehow drives the periodicity of the ice age cycle. And the first one is eccentricity, and this is the only one that actually changes the total amount of energy hitting Earth. And this is just sort of how elliptical our orbit is. And this varies slowly. Here is a plot showing how the eccentricity has varied over the last, I guess this would be billion years? Million years. And so you see these sort of swings here. And then right below is the calculated global mean insolation variation based on this. And I mentioned earlier that it's small, and so this is between 342 to 343, so less than 1% change.
What causes that?
So the orbit isn't perfectly circular, in part because of the large other bodies, planetary bodies. Jupiter, and yeah, so it's slightly elongated, and that kind of moves back and forth a little bit. The second one, the second orbital parameter that changes is kind of the tilt of the Earth axis, the spinning axis. So right now we're tilted at, I think it's 23, 22, and it varies between 22.1 and 24.5. And so this is just sort of how tilted the northern hemisphere is towards the sun at its most tilted position. So this is the sun here. The tilt kind of works like this. So when you're over here, the northern hemisphere is pointed towards the sun, and when you're at this point here, the southern hemisphere is pointed at the sun. And so this varies over time, and this changes sort of how much insolation, how intense the insolation is during the northern hemisphere summer. So the northern hemisphere summer is when you're pointed towards the sun. If you're pointed more towards the sun, then you're going to get more insolation at 65, 70, 80 degrees north. Yeah.
What causes that variation in tilt, and is it regular?
Don't know if I have a slide. It's not perfectly periodic. There are sort of a complicated picture, and it has to do with how Earth initially formed. Ours is more regular than Mars, and that's in part because of the moon. The moon sort of provides some stability and doesn't allow for a complete flip or a rotation greater than a certain angle. So this is actually fairly stable relative to others. Yeah.
Can you explain why it would be more insulation when the angle is steeper?
Yeah. So I said that the flux is about 1366, but that's if the flux is hitting the surface perpendicular. As the surface becomes inclined, the amount of energy hitting that surface decreases. So you can think of a,
It's a sphere, it doesn't matter.
sure, but, oh yeah, so the total energy doesn't change, but the energy incident on the northern hemisphere during the summer does change.
Okay.
Yeah, so the only orbital parameter that affects the total energy is eccentricity, because that's affecting the net distance from the sun. The next two, the obliquity, so the tilt, and the precession just affect the distribution of incoming insolation. So the final sort of orbital parameter is precession, and this is just this kind of combines the tilt with the eccentricity, and saying that during our orbit around the sun, there is one time where we're closest to the sun, and then one time where we're further away from the sun. And it matters if you're pointed towards the sun when you're closest versus pointed towards the sun when you're furthest away. So the time that we think is sort of the best chance for getting out of a glaciated period is when you're tilted a lot and you're pointing towards the sun or you're closest to the sun during your summer. So that would be this case here. So summer solstice, pointing towards the sun, and the sun is closest to you. The time when we think that that you're most likely to fall into a glaciation is this time up here, where your summer solstice is pointing towards the sun, but it's furthest away. So you're going to be getting, and then you combine that with a lower tilt, and so then you're getting really very little, or comparatively little, insolation in the northern hemisphere during the summer, and the ice can kind of, the seasonal snowfall can sit around for a while and slowly build up ice sheets. I'm going to go through these first two very quickly. There are three main sort of early ideas, models for how the variation in our parameters can lead to changes in glaciation. The first was proposed by Adamar. It was very early on, and it was just thinking about this precession idea. And 1840s. And so this is this idea that yeah, sorry, I should have included the dates. That the glaciation just switched back and forth between northern and southern hemispheres. Kroll then took it sort of one step forward and said that it's not just a simple seesaw, you need to take into account the eccentricity, and that it's about sort of a total change in amount of energy that's hitting Earth. The person who these sort of cycles are named after, Milankovitch, came along in the early 1900s, and he did the full-on calculation. He was the first person to calculate the distribution of insolation on the top of the atmosphere, and then also to look at how that changes as you change the orbital parameters. And so he focused on insolation at 65 degrees north to get changes in northern hemisphere glaciation. The problem with this theory is that while it does predict some of the periodicity in the cycle that is observed, so we have this 41,000 year period that we see in the ice record, and a 100,000 year period in the ice record. 100,000 year period is the period of eccentricity, and 41,000 years is the period of obliquity. But if you look at changes in insolation, most of the biggest period that change is occurring on, if you look at just the orbital parameters, is the precession, and that's 20,000 years. And that doesn't really show up in our climate record at all. So, but I mean, the other variations of 41 and 100,000 years are in the orbital, sort of the insulation derived from orbital parameters, but they're not the main periods that matter. So there's somehow a mismatch between what we think is this forcing and what's important in the forcing and what the climate feels is important. Yeah.
I may be the only one, but I've lost track of how you're defining insulation.
That's because I'm not sure if I fully described insulation. Insulation is incoming solar radiation, and I'm defining from here on out that to be just at a particular latitude. So not this global value that is hitting the surface of the Earth at the top of the atmosphere, but what's actually hitting the planet at a particular latitude averaged over the whole year. So your insulation is going to vary as a function of latitude. And Milankovitch and a few other people before him suggested that looking at the amount of insulation hitting the northern hemisphere where you had ice sheets is what's going to be important for thinking about how ice is going to respond to changes in insulation driven by changes in these orbital parameters. So there's a match between the periods here, but not a match in terms of the amplitudes or which periods are most important. So I'm running out of time. Fast forwarding quite a bit here, there becomes this idea that maybe this whole idea of even just these smooth transitions where you have smoothly varying temperatures with smoothly changing orbital parameters isn't quite right. More and more evidence as you get finer and finer detail on the climate record shows that some of these transitions in temperature from the glacial to the interglacial can take place in 10s, 20s, hundreds of years. So much, much faster than the change in orbital parameters. And so there's this idea of a threshold becomes introduced. That as soon as you get insulation drops even just a 0.1% below some level, you can start to form ice. But above that, you won't. And ice is going to start to melt if you get above a certain threshold. This idea that the climate responds non-linearly to changes in these different parameters. And so this is sort of one of the better models, better simple models. It's still not super simple, but I'll try to walk you through it. This is a 3-level of glaciation model. So you have interglacial time period, which is this top level, and you can kind of think of these as just sort of levels or plates, and maybe like a waterfall. And then you have a time period where you have small glaciers, and then a time period where you have full glaciation. And so insulation varies along sort of this direction, and ice volume increases in this direction here. And so you're sitting up here in an interglacial period, and the insulation at 65 degrees north starts to decrease. At some point, it hits some threshold and just falls down, and you start to form glaciers. And it'll form small glaciers for a while. The glacial volume will increase slowly, even as the insulation is changing. And at some point, you drop off onto this big glacial region here. And this transition happens, it can happen both directions, but here it's indicated as happening by growing ice sheets large enough that you all of a sudden grow really big ice sheets. And then if you start to increase the insulation past some level, you pop back up here. And so this is kind of combining this last transition is throwing in a bunch of ice dynamics into trying to understand why you can quickly lose a larger ice sheet faster than you can lose a smaller ice sheet. I'd be happy to talk more about that with people at the end of the talk. Just sort of the second to last slide here. If you use this model and kind of compare what you would predict sea level to be using the model versus what's observed, it's a little bit hard to see maybe in the back, but you start to see that the amplitude and the periodicity is beginning to really match using this very, well, not totally simple, but relatively simple model of a three-tiered sort of cutoff and abrupt transition model with a nonlinear climate feedback. And this is again showing really just the same thing, that the amount of variation and the amplitude and variation as a function of frequency for the model, which is the solid, and observations, which is the dashed, begins to really match when you use this sort of cutoff transition model. So to wrap things up and conclude, in the very beginning I said that we live happily in this habitable planet, but that at early times during the formation of Earth, it might not have been so simple to get us into that habitable planet. There are a wide range of temperatures and climates that Earth is habited, ranging from these very, very cold to very, very warm. And right now we're sitting somewhere in the middle in what's called an ice age Earth, where we have some small glaciers both in the northern and southern hemisphere. And that small changes in the orbital parameters are driving changes in our climate through a complex system of sort of abrupt transitions and nonlinear feedbacks. And sort of this is kind of leaving you back where Tom is going to pick up again, starting to talk about some of the ways in which and where you get planets, and how this all feeds back into where solar systems, or how solar systems form. Yeah?
As the ice is lost from the Antarctica, like the continent rebounds, how does that affect the rate at which the ice continues to melt or move?
In a non-trivial way. Antarctica is really very large and changes, we think, pretty slowly. And the ice isn't flowing very fast there. So not as big of a change there. In terms of when you think about the large ice sheet that was present here, as that started to retreat and as you started to have changes in rebounds, there you do get some significant changes in the topography, which could feed back. I don't know how much. You're probably talking, I'm not sure how much. But, yeah.
Can you remind us once more what triggered the onset of the molecular cycles?
Well, I think that the variations in orbital parameters were always there. But what sort of triggered the glacial, interglacial period was just that probably CO2 levels got down low enough that you can start to form ice when the orbital configuration is such that ice can slowly start to form.
So if we loosen up CO2,
we could perhaps stave off the next ice age. Yeah.
get out of the cycles.
Get out of the cycle, prevent the next glaciation from happening.
Are there any thoughts on what determines the threshold for the nonlinear changes?
Not any simple ones. I mean, the model that I showed here basically tunes that threshold so that we get an answer we like. A lot of the effort that people are starting to do in glaciology is trying to get an idea of what sort of feedbacks there are and how does melting affect how you start to absorb energy and all that. But it's not going to be a simple number in the end. It's going to be a big complicated model, and whether or not that gives any more insight than tuning a very simple model to the actual observations, I don't know. I'm back yet.
Topography notwithstanding, perigee always occurs in the summer in the southern hemisphere. Wouldn't that indicate that Antarctica would be more susceptible to increased radiation?
It might. I mean, Antarctica is just so cold that it's not it's not near a threshold where you get a lot of melting. You know, the ice is a little bit further north in Antarctica than it got in the northern hemisphere here. We have ice down here, which is 44 degrees north, and Antarctica stops at 68 degrees south or so, I mean, apart from the peninsula. So, you know, you can change the climate there a little bit more, and you're still well below freezing. Whereas here, you change the climate a little bit, and you bump up above freezing, and you start to melt the ice. Question? Yeah.
Well, of course, we hear a lot about global warming and greenhouse gases, and some alarmist reactions to the rate of deglaciation. Is it your right that we've reached a threshold anomaly or changing one?
People are certainly talking about thresholds, particularly in terms of sea ice, is where a lot of that discussion is happening for right now. I don't know that we really know the next threshold for Greenland, for example. I mean, that's the one where Greenland is one of the places where glaciologists are really concerned about what's going on, and we are seeing sort of rapid changes there. Yeah, there are a couple different thresholds. There's one threshold which you hit, and then basically Greenland is going to slowly melt, and I don't think people really know where that threshold is. I don't think we're there yet. The sea ice in the Arctic, we could be close. Models are suggesting that we might be teetering on some sort of a threshold where we don't get summer sea ice in the future. Yeah.
You're using an isothermal Antarctica as a thermometer, do I understand?
Yeah, so I tried to sweep all of that under the rug today. But the basic idea there is that if you put 120 meters of sea level equivalent ice onto the continent, that ice is going to be isotopically light, and the ocean will become isotopically heavy. And so that's the variation there. It's complicated because the isotopic ratio is recorded in what's called benthic foraminifera, which are little calciphoric creatures that live at the sea floor. And the rate at which they incorporate isotopically heavy water or oxygen into their calcium is also temperature dependent. So it's not a simple proxy. I mean, none of these proxies are simple. And they all take sort of someone with a very simple idea and then 30, 40 years of tweaking with it and coming up with various different corrections to get our current best guess.
Well, it discourages me of thinking that the politicians that we have are such idiots, because this is hard to understand.
It's not simple.